You can make it as messy and complicated as you want. Generally, for this course, we're going to assume that it's a plane wave, we're going to assume that it's a harmonic wave, and we're going to assume that we are travelling along one of the axes, the X, the Y, or the Z axis, so that we can just simplify the maths and keep things, keep the maths as nice and simple as possible, basically. Electromagnetic waves, which for lasers and light and optics, they represent a small region of the electromagnetic spectrum, and they are described by electromagnetic waves. An electromagnetic wave is a wave which comprises an electric field and a magnetic field. It's not that you have two separate things. Okay, it's not an electric field as well as travelling alongside it. It just happens to be a magnetic wave. They are a single electromagnetic phenomenon which is travelling along in some direction. Okay, electromagnetic waves, you can have the electric part or the magnetic part independently, otherwise it's not an electromagnetic wave, obviously. So this figure below shows that we've got an electric field E, and in this case it's pointing along the y-axis, it's polarised along the y-axis, and we have a magnetic field B which is polarised along the x-axis. And the first thing to notice is that these are perpendicular to each other. Okay, they're always perpendicular to each other. The electromagnetic wave, the E and the B fields, are always perpendicular to each other, and they're always perpendicular to the direction of travel as well. Okay. The other thing to notice is that they're in phase, and that remains the case as it travels through space along the z-axis. They always remain in phase. And these waves then, we generally refer to these as transverse waves, because the oscillation of the electric and the magnetic field is transverse to the direction of travel. In some books you will see this referred to then as TEM waves. TEM just refers to it as being a transverse electric and magnetic field. Okay, a wave. So the way that we describe this wave is that it has an electric component and a magnetic component. We use E to denote the electric field, B to denote the magnetic field, and we have to then think about if that wave is travelling through some medium or through vacuum, what are the electric properties of that material or the vacuum, and what are the magnetic properties? Because that's obviously going to affect how the electric field we see it manifest itself. So we have to think about the electric and magnetic properties. If it's travelling through a vacuum, then these are of free space. It's referred to as free space, and that then is given the symbol epsilon naught. That's the electric permittivity of free space. And if it's going through some material like air or water or glass, then we use epsilon, and that's the electric permittivity of that particular material. That's the electrical properties. Also for the magnetic properties, then we think about it in terms of mu naught, the magnetic permeability of free space. And for any particular material, then again, the magnetic permeability of that particular material, of that propagation medium, the medium through which the wave is actually propagating. We can also express these in terms of, for any given material, how it relates to the basic electrical and magnetic properties of the vacuum. So when we have an absolute vacuum, then we have an electric permittivity of epsilon naught. For some other material, glass for example, then what we'll find is that the electric permittivity of that material is just a constant times the value for the vacuum, and the same thing for the magnetic relative permeability. So our dielectric constant K refers to the how many times the vacuum permittivity, the value, the electrical properties are for that particular material, and similarly for the magnetic properties, the relative permittivity for electrical and relative permeability for magnetic. Okay, this is all very exciting, of course, but we come now to one of the great achievements within science and engineering, the work of James Clerk Maxwell, and he figured out that the relationship between the electric and the magnetic field is interdependent. Okay, you can't have one without the other. In fact, instead of having an electric field and a magnetic field, you have an example of a unified field. So any changes in the spatial variation, any spatial variations in the electric field will give you a time variation in the magnetic field. Any spatial variations in the magnetic field will give you a time variation in the electric field. Okay, so these four equations remarkably and incredibly impressively describe everything that you need to know about any electrical or magnetic equipment, from motors to light to anything involving electromagnetics. All of it can be described and derived from these four equations, which is quite remarkable if you think about it, just those four equations. I mean, they're not particularly complicated, and so it's amazing that such a simple set of equations are so inclusive. You'll be glad to know that I am not going to spend much time working on Maxwell's equations. We'll see that they are consistent with the wave equation, but we won't be bringing them up any further than we need to. So, magnetic field which changes in time gives us an electric field which changes in space, and vice versa. The electric and the magnetic fields are intrinsically dependent on each other. And the E and the B parts are mutually sustaining. You can't have one without the other one. Okay. For waves travelling in a vacuum, then there's no electrons, there's nothing to conduct, there's no current that can flow, and so the current density, there's no electrons floating around, and so the current density J is 0, and the free charge density rho is 0, and you can then look at the equations and from them derive an expression which looks like this. Now, this should hopefully look familiar to you. What we've got is del squared of a particular item is equal to a constant times d2 over dt squared of that same item. In other words, what we have is equations which look like the wave equation for both the electric field and the magnetic field. And again, we can sort of break these down into x, y's and z's and make it horribly complicated and messy looking. But one of the things that we should notice here is that this constant, before what we had is the constant was 1 over v. And now what we're saying is that the relationship here is the del squared is equal to d2 over dt squared is related through this constant, and this constant is epsilon naught times mu naught. So again, the fundamental properties of a vacuum, and so the speed of light in the vacuum is given by 1 over the square root of epsilon naught times mu naught. If we've got a wave travelling in the z direction, then again from these equations we can show that the electric field and the magnetic field are related, and the relationship is given by a constant, and that constant is the value of the speed of light c. And the speed of light c is around about 10 to the 8 meters per second. Quite a large number. It's 3 times 10 to the 8 if we want to be closer to the truth. And so the electric field is 10 to the 8 times bigger in amplitude than the magnetic field. Okay, so the electric field is about 10 to the 8 times bigger than the magnetic field in the amplitude, in terms of the amplitude. Now, given that that's the case, that the magnetic field, the amplitude of the magnetic field is 10 to the 8 times smaller than the electric field, generally for electromagnetic waves, we just ignore the B component, the magnetic component, completely. Generally, the sorts of materials like glass and plastics that you use in optics and lasers are not strongly magnetic materials. So you have a weak magnetic material and a very weak magnetic field, so we can assume therefore that the electromagnetic wave is effectively well represented just by the electric field alone.